We're going to start with the presentation of all the facilities now.
Large-scale triaxial apparatus
Yeah, thank you. If we can start. Malika.
is a kind of multi-purpose device consisting of large loading frame with two capable hydraulic pistons. One of them is installed in axial direction, while the other provides loading in horizontal direction at the bottom of testing specimen. The axial load is measured by load cell attached at the top cap in order to eliminate the effects of piston friction. Very high accuracy level of load and displacement control enables characterization of different geomaterials, for instance stiffness or damping of materials at very small strain ranges. Axial and lateral strains are measured by LVDTs placed in various positions on the specimen. Measurements of local small strains up to 10⁻⁵ in both directions are enabled. Furthermore, accelerometers can be attached on the specimen to measure shear wave velocities, and also optical system for displacement measurements can be used during the specimen loading. Dimensions of frame allow testing of prismatic specimens with height up to 80 centimeters and cross sections 40 × 40 centimeters. Monotonic or cyclic loading is possible in triaxial mode, direct shear mode, that means testing of friction characteristics, and simple shear mode. Specimen is installed within the rubber membrane, so the confining pressure is applied by means of a partial vacuum as back pressure and is limited to 100 kPa. Rigid confining frames are used for simple shear mode, enabling K0 stress state during the axial loading. The capability of simple shear apparatus can be used also to apply the loading with controlled principal stress axis rotation. So synchronized vertical and horizontal cyclic loads enables the simulation of traffic loading without a moving wheel. Large-scale triaxial apparatus is located at the Slovenian National Building and Civil Engineering Institute in Ljubljana. This device was developed in-house during last decade, and we add new features to it every year, depending on current research needs in lab. My name is Stanislav Lenart, and I will coordinate possible research proposals involving testing with this device. Me and my team are looking forward to welcome you in Ljubljana.
Good morning. My name is Amin Askarinejad. I'm Associate Professor of Experimental Soil Mechanics at TU Delft, and in the following slides, I'm going to introduce our geotechnical centrifuge, its actuation and sensing capabilities, as well as the type of projects which this equipment has been or can be used for. The geotechnical centrifuge of TU Delft is a symmetric beam centrifuge with a maximum payload of approximately 300 newtons. The nominal radius of this device is 1.22 meters. The effective space available on baskets on each side is about 40 × 40 × 50 cubic centimeters. Maximum design acceleration is 300 G. However, most of the electronics have been tested at up to 150 G. The data logging system is equipped with 50 high-speed logging channels. In terms of instrumentation, the device is equipped with a wide range of miniature sensors such as potentiometers, laser displacement sensors, pore pressure transducers, soil pressure sensors, load cells, strain gauges, and high-resolution, high-speed digital cameras suitable for image analysis. This centrifuge is equipped with several general-purpose or specific actuators. On the right-hand side of the slide, we see a schematic of the fully controlled VHM actuator, which applies loads to models at either displacement or load-controlled conditions. On the left-hand side, we see a photo of a specifically designed actuator to simulate the static liquefaction of submarine slopes. The geotechnical centrifuge of TU Delft has been used for a wide range of applications such as installation and long-term performance of monopiles, spot cans, and suction caissons as foundations for offshore renewable facilities. Other examples such as impact pile driving and silent offshore pile installation techniques, stability of dikes and embankments, responses of retaining structures, slope stability studies, land subsidence, flow in porous media, are all other examples of applications investigated using this centrifuge. This facility is located at the Department of Geoscience and Engineering of Delft University of Technology in the Netherlands. For more information, please consult our website or contact me at a.askarinejad@tudelft.nl. Thank you for your attention.
Hi everyone, I would like to introduce you at this point to the Geotechnical Centrifuge Center at ETH in Zurich. Our drum centrifuge, established by Professor Sarah Springman in 1999, was manufactured in the UK by Broadbent and has a radius of 1.1 meters, being one of the two biggest drum centrifuges in the world. A unique feature of the drum centrifuge is that its entire circumference can be used as a soil container. Combining this feature with its ability to spin up to 440 G allows researchers to investigate very large prototype problems up to 132 meters depth, 300 meters width, and 2.2 kilometers length. A pair of multi-purpose actuators are available for in-flight model creation, construction processes, site investigation, and load applications. Multiple arms can be attached to the actuators to perform different functions depending on the scope of the experiment. Furthermore, a climate box is available, capable of simulating rainfall as well as model saturation systems. Our Geotechnical Centrifuge Center is being developed by the addition of a new beam centrifuge, which can be seen here in the lower side. This was built by Krupp in Germany and has an outer radius of 4.5 meters and a maximum capacity of 500 G tons. The centrifuge, which in the 90s was under operation at the university in Bochum, underwent a complete refurbishment and is currently being installed at ETH Zurich. This centrifuge will be capable of modeling advanced problems such as seismic shaking under enhanced gravity field or coupled hydrogeotechnical processes, as well as other typical geotechnical problems related to infrastructure. Some of the selected experimental setups from the drum centrifuge that have been used successfully in our laboratories include applications such as foundation testing with bearing capacity tests for shallow footings, pile groups, and further foundation systems on level or inclined ground with scoured or unscoured soil surfaces, pushover tests along monotonic or cyclic load paths for a variety of adjustable superstructures, and combined loading for experimental determination of failure envelopes using constant vertical load or constant vertical displacements. Further applications are slope and dam stability with the possibility of transient hydraulic loading or controlled precipitation simulating extreme weather events. And last but not least, structures on soft soils, focusing on consolidation and settlement related problems and soil improvement techniques. For our beam centrifuge, some of the most important setups include a dynamic shaker for horizontal seismic loading under enhanced gravity field and a miniature tsunami generator for the investigation of fully coupled hydromechanical response of structures subjected to wave loading. For further detailed information about our experimental facilities and their capabilities, I encourage you to get in touch with Professor Ioannis Anastasopoulos, Head of the Chair of Geotechnical Engineering within the Institute of Geotechnics at ETH Zurich. Thank you very much.
Good morning. My name is Amin Askarinejad. I'm Associate Professor of Experimental Soil Mechanics at TU Delft. In the following slides, I'm going to introduce our large-scale geotechnical physical modeling facility, also known as the Geotank. I will briefly explain the actuation and sensing capabilities, as well as the type of projects which this equipment has been or potentially can be used for. The Geotank is a 2-meter wide, 2-meter high, and 5-meter long inclinable structure with transparent sidewalls. The instrumentation setup includes various types of sensors and actuators. An example of a miniature sensor which includes a triaxial accelerometer and one pore pressure transducer is shown in the picture on the left. This sensor is less than 1 cubic centimeter large and has a designed unit weight comparable to fluidized sand, which makes it floatable and mobile during sample preparation. All sensors and actuators are connected to the central control and data acquisition system. This system allows for a switchable sampling rate ranging from 1 Hz to 100 kHz, allowing to optimize the size of the recorded data files. The base frame, 2 hinges, and an electromotor all enable the tank frame to be rotated. 4 sets of base isolators under the frame are installed to prevent possible external vibratory triggers. The geotank is equipped with a fluidization system to prepare sandbed in a loose and uniform state with a thickness ranging from 0.1 to 1.5 meters. The sandbed in the geotank can be further prepared by controlled dredging of a slope through a Venturi-based suction dredging system. The geotank has been designed to test several types of failure triggers, such as tilting, a shock load on the crest of the submerged slopes, and controlled hydraulic pressure injection from the base of the tank. This unique facility has 2 wave absorbers that are installed on both inner walls. These wave absorbers minimize the reflection of shallow water waves. This feature makes it possible to study tsunami wave generation due to submarine landslides. The geotank of TU Delft has been used for many applications, such as static liquefaction in submarine slopes, protection layers against seabed scouring, and submarine landslide-induced tsunami waves. The geotank, however, can be used to physically model a wide range of other geotechnical applications, for example, offshore geotechnical engineering, dredging in sand layers, dikes and embankments, soil structure interaction, slope stability analysis, unsaturated soil mechanics, soil vegetation interaction, and last but not least, dynamic effects on geotechnical structures. This facility is located at the Department of Geoscience and Engineering of Delft University of Technology in the Netherlands. For more information, please consult our website or contact me at a.ascarinejad@tudelft.nl. Thank you for your attention.
The geotechnical centrifuge of the University Gustave Eiffel is used for performing tests on small-scale models of geotechnical works. This large centrifuge can run a 2 tons instrumented model at 100 G. It is a versatile equipment in which various research have been performed, such as mitigation of ground vibrations, lateral loading of flexible piles or monopiles instrumented with strain gauges or fiber brag grating sensors. Recent applications are connected to marine renewable energy or soil improvement with rigid inclusions. The Uni-Eiffel geocentrifuge, located in the French Atlantic coast, has developed for decades a know-how in physical modeling. A large set of ancillary equipments used in the lab at 1G or in flight are available. For instance, hydraulic and electric actuators can control cyclic loading on foundations. About 230 sensors are regularly used for macrogravity experiments. The soil reconstitution, mainly sand or clay, is performed in the lab, but in-flight investigation is possible for characterizing soil profile. Other onboard equipments are available, like a 4-axis robot. The team includes 6 researchers and 5 technicians in the laboratory devoted to centrifuge for geotechnics. The Geolab is directed since 2021 by Dr. Mathieu Blanc and involved in several research projects funded by public agencies or private partners. The Nantes campus of the Uni-Eiffel is located in the countryside, 50 kilometers away from the seashore. There are about 300 people working on the campus, giving the opportunity to meet other researchers, for instance, in the restaurant, where the 2 chefs use sometimes strange cooking tools.
The geomodel container measures 4 times 2.5 times 1.2 meters. The container is equipped with utility frames to hold plungers, hoisting equipment, and measurement sensors. The container allows for phreatic or confined groundwater flow. Effective stresses at large depths can be simulated using different air pressure levels. The geomodel container can be downsized if required. The container itself is very flexible and can virtually be used for any test that requires a sand bed up to 4 times 2.5 times 1.2 meters. The container is also equipped with a fluidization system for building homogeneous sand models at the required density. The model container can be filled with granular material or clay. It is possible to insert constructions in the container to examine the soil construction interaction. The staff on the facility has experience in making homogeneous or deliberately layered soil samples. An overview of the systems, utilities, and equipments that are available for the geomodel container is given in this table, together with a brief description of their technical specifications. A hydraulic, vacuum, and pressurized air system is available. An excavator is present for quickly replacing sand if needed. The infrastructure is equipped with an HBM data acquisition system. For the geomodel container, a common and wide range of sensors is available. This table provides a brief overview of the parameters that can be measured. Since the instruments are regularly updated and/or replaced, the most recent sensors possibilities should be checked before preparing a test. All sensors can be calibrated in-house and are traceable to international and national standards. As aforementioned, the geomodel container has been used in various research projects. An example are tests performed on sinking ground structures. In this project, the buildup of pressures on gas pipes due to ground subsidence has been investigated in the container. Another research project in the facility was the investigation of the effects of liquefaction on pipelines. Tests were run in the geomodel container with the objective to determine the liquefaction time and the resistance against pipe uplift. For the experiments, a thick, full saturated loose sand layer was built up. Liquefaction was caused by the impact of a falling weight on the sidewall of the sand container. The Deltares geocentrifuge. Starting with the technical specifications, the Deltares geocentrifuge is a C72-3 beam-type centrifuge manufactured by Actidin. It has a 260 G-ton capacity and a platform radius of 5 meters. The geocentrifuge is equipped with several systems necessary to perform experiments. The test control system is designed to perform any remote action that could be needed during centrifuge testing. The system is completely designed and built by Deltares and uses hardware and software from National Instruments. For the data acquisition system, HBM modules are chosen in combination with Catman AP software. The centrifuge is equipped with high-speed cameras, monitoring cameras, and fixed on-board cameras. The high-speed cameras can, for instance, be used to capture events during dynamic experiments. The centrifuge is also equipped with cylindrical and rectangular storm boxes. These storm boxes are structurally reinforced to minimize mechanical deformation during flight and can also be used as consolidation cells. The centrifuge is also equipped with a 4D robotic system. This system provides actuator and tool flexibility during flight up to a G level of 100 G. The 4D robot creates the possibility to use 4 different tools on any location, covering almost the whole surface of the centrifuge basket during flight. For the centrifuge, several utilities are available to facilitate soil model preparation using different types of soils, both cohesive and cohesionless. For the preparation of clay samples, the clay slurry mixer and the consolidation frame are available. The clay slurry mixer allows the preparation of a slurry by mixing clay and water under vacuum. For consolidating the clay slurries from the clay mixer, the consolidation frame can be used. On the other hand, for the preparation of sand models, the sand rainer can be used. With the sand rainer and an appropriate choice of sand flow and falling height, it is possible to obtain a variety of densities, from loose to very dense.
Het is wel een hele unieke onderzoeksfaciliteit, waar wij met onze eigen expertise natuurlijk zaken in gaan onderzoeken.
De centrifuge die vandaag geïnstalleerd is wel een specifiek geval. Met een platformradius van 5,5 meter is het een flinke. We kunnen daar gewoon schaalmodellen in beproeven alsof het werkelijke modellen zijn. Dus alsof het gewoon iets vergelijkbaars is met in het veld. En dat is eigenlijk het grootste belang van de geocentrifuge.
I'm Dr. Sam Stanier, Senior Lecturer in Civil Engineering at the University of Cambridge, and I'm going to introduce you briefly to the Schofield Centre, which specialises in geotechnical construction process modelling. And this is the contents of this brief presentation. I'm going to introduce the 2 centrifuges that we have, our sample preparation facilities, strong boxes, actuators and other equipment, and I'll finish with a short example looking at tunnel model. Now, the centrepiece of the Schofield Centre is the Turner beam centrifuge, which is a 10-metre diameter machine with a 150 G-ton payload capacity, which typically operates at between 80 and 100 G. The beam centrifuge has a comprehensive slip ring stack with capacity for air, fluids and fibre optic communication. The second major facility at the Schofield Centre is the mini drum centrifuge, which is a diameter of 1 metre and can operate at up to 400 G. The channel is 220 millimetres wide and 150 millimetres deep and can be operated on a drum or with small boxes, some of which are equipped for PIV testing. Again, there's a fibre optic slip ring facilitating the use of fibre optic strain measurements. In terms of model preparation facilities, for sand we have a programmable sand pourer which can closely control the relative density of sand deposits and generate repeatable samples. For clays we have an array of hydraulic and pneumatic presses. In addition, we have CO2 and vacuum-based sample saturation facilities. There is an array of strong boxes, from simple circular tubs and PIV window boxes to strong boxes specifically designed for modelling construction processes and earthquake testing. The Schofield Centre has a number of 2D and 1D robotic actuators, syringe pumps and the like, which can be used for model tunnel volume loss control, and 2 actuators for geotechnical earthquake engineering research, the Stored Angular Momentum or SAM actuator, which can execute sinusoidal shaking events, and a servo hydraulic shaker, which has been developed to allow for the modelling of more realistic seismic events. Cambridge has a long history of developing digital imaging techniques for geotechnical applications, and we have a camera system for both quasi-static and dynamic testing, as well as numerous Raspberry Pi camera arrays, which can be used for both conventional 2D imaging using PIV and 3D imaging using point cloud techniques. And we've got an example here on the left-hand side performed in the mini drum centrifuge, which used an array of Raspberry Pi cameras to image the failure mechanism as the sandy slope was loaded by the vertically loaded foundation at the top of the slope. Now, tunnel modelling is very active in Cambridge, and we have apparatus for tunnel structure interaction modelling, again with PIV capabilities. The tunnels are modelled with controlled volume loss apparatus, including staged volume loss variants, and a mini tunnel boring machine is currently in the final stages of development and commissioning for both use in sand and clay models. Now, thank you for listening. The main point of contact for the Schofield Centre is Professor of Infrastructure Geotechnics Giulia Vigiani, and we look forward to working with you as part of the Geolab Transnational Access Programme.
If you want to test soil structure interaction or any other geotechnical problems in medium to large scale, then you should have a close look at the geotechnical test pit at Technical University of Darmstadt. Here you can see a photo of this test pit. It has a total length of about 20 meters and a width of about 5 meters. It has two parts, a more shallow part which has a depth of about 3 meters and the deep part which has a total depth of 6 meters. Within this test pit, we mainly use sand as our test material. So this sand can be dry pluviated to reach very homogeneous samples, but we can also test in saturated conditions, which is feasible here within this steel container. This steel cylinder has a total diameter of 4.3 meters and a depth of 3 meters. Here you see some load actuators which are typically attached to such loading frames. You can see here in green, and those loading frames can be moved across the whole pit and can also be inclined. So which type of foundations are we focusing on? Within Geolab, we are mainly focusing on the soil-pile interaction, and you can study here within our pit the behavior under static and dynamic loading. And like I said before, our load frames can be inclined. We have them vertical, but we have them also horizontally or in another inclination. So that means you can also load your piles in different angles. But not only single piles can be investigated, you could also test pile groups, for example, and evaluate the pile group effects, because the size of our pits allows some scaled models of pile groups. But not only pile groups or single piles, of course you can also test and evaluate pile installation effects. Of course, to evaluate pile installation effects you need to have a proper equipment to install piles. We have some available for vibrating and also for hammering, but of course, this also depends on pile sizes. But not only piles can be investigated in our pit. Here within Geolab, you could also have a look on any other type of structures and the soil structure interaction. For example, you could test new types of foundations and could test some prototypes. You could have a look on ground improvement methods, but also have a look on other structures like, for example, shallow foundation embankments or buried structures like pipes or cables. And if you want to know more about this geotechnical test pit at TU Darmstadt, you can contact either directly me, Hauke Zachert, or our Geolab project manager, which is Dr. Beroya Eidner. And we are looking forward to welcoming you in Darmstadt.
CEDEX track box is a 21 meter long, 5 meter wide and 4 meter deep testing facility whose main objective is to test at 1:1 scale complete railway track sections of conventional and high-speed lines for both passengers and freight trains at speeds up to 400 km per hour. The simulation of the effect of the passing by of a train in a test cross-section as it occurs in a real track section is performed by application of loads by 3 pairs of servo-hydraulic actuators. The railway track response in terms of displacement, velocities, accelerations and pressures is collected from different instrumentation, such as LVDTs, geophones, accelerometers and pressure cells. With all this information, we can derive, for instance, the track stiffness. The instrumentation can be installed inside the embankment and the track bed layers, ballast, subballast and foam layer, and also on the different track components, rail, sleeper and rail pad. Fatigue tests, in which we can apply some millions of axes, are the most interesting tests that can be performed in our facility. Doing so, in around 10 working days, we can model the effect of the passing by of trains during a year in a real section. In those tests, we can analyze the mechanical behavior of new materials, such as prototypes of sleepers and slab tracks, as seen in the left-hand side photographs, or different types of materials for the ballast and subballast layers. The central photograph shows a test in which ballast layer was completely fouled with sand, as happened in desert areas, to determine the effect of the sand in the behavior of the ballast layer. Another field of interest is the analysis of the behavior of the current track configuration when the commercial train speed is increased up to more than 300 km per hour, as it has begun to be planned in some European countries. Figures below show results of this kind of test in which the increase of rail displacement with train speed can be determined and the track critical velocity can be deduced. In this third slide, you can find some useful information to contact us if you want to use our testing facility to perform some tests. We will be very happy to help you with your proposal. Thank you very much for your interest.
Sorry, just a quick note from ourselves. The next presentation is a video on YouTube. We will pop the link in the chat, just in case there's some connection problems on your side and the video is lagging. Thank you.
Critical infrastructure such as roads, railways, and bridges are increasingly being built on difficult ground conditions today. Problematic geomaterials such as soft clays, silt, and loose sands are encountered in almost all modern development projects. The problems are also intensified due to climate change, aging of structures, and natural hazards such as landslides and earthquakes. Over the years, the Norwegian Geotechnical Institute has developed a system of geotechnical experimentation test sites with a wide range of geological ground conditions. These sites are used to verify different solutions in geotechnical engineering and to calibrate our tools. The sites are the soft clay site at Onsøy, the silt site at Halden, the sand site at Øysand, the quick clay site at Tiller, close to Trondheim, and the permafrost site on Svalbard. Also, we have an avalanche testing facility at Fonbu, Ryggfond. At the NGI Geotest site facility, each experiment is designed, built, and custom made to meet the needs of our clients and users. The NGI has a strong expertise and also strong background in field investigation and large-scale model testing in the field. For more information, please don't hesitate to contact us.